Okay, so I'm going to go over the some of the lab, some of the homework assignment. Again, I'm not going to make a whole new lab. I'm just going to show you kind of how to do some of the things. So a lot of what we're going to be doing is going to be a repeat in some sense of what we did last week. So what I mean by that is, the incomplete orthogonalization method is just going to be like the normal orthogonalization method, but we only orthogonalize with respect to a few of the previous vectors. So it's not really going to be anything that is, a lot of what we're doing is just a repeat of what we did before. I think one difference is this is a different matrix that I've have you set up. So we can still just copy and paste what we had before though. So that's what I'm going to do here. This is essentially, I don't know if this is exactly what I had before. I think before the name of the function that made the matrix was like, I'm getting confused on what I'm looking at now. I think the name of the matrix or the name of the function that made the matrix before was like I don't know. Anyways, here it's make large 3D problem. So I'm going to put it here. Don't think I've run this yet, so let me run this. And again, I'm on Jupyter instead of on Google Colab. So now let's just run this. Yep, and that looks exactly like what we're expecting, so everything's working well there. Okay, so what we're going to do here is just an incomplete Arnoldi step, and it's going to take this this parameter k here. And so what we can do, like I mentioned, it's very simple. We can basically just copy and paste exactly what we had last time, and then just modify it a little bit. So I'm going to copy and paste what I had before. Let's see, hold on one second. I think this is just exactly what I had before here. Okay, so this is just the standard Arnoldi step. But notice the only difference is it's taking in a parameter k, and where does that come into play? Well, it's going to come into play right over here in this. That should say, ordinarily it just said range of j. That's what it did say. But we want it to go from j minus k to j. Now, it's not j minus k plus 1 because it's not going to go up to j. It's going to go everything up to, but not actually get at j. So it's going to go, if we just have this right here, this is going to go 0, 1, 2 up to j minus 1. So we need this to be j minus k. But of course, j minus k could be negative. So it's going to be max of 0 and j minus k. Okay, and that is the only change that we need to make. Whoops. Excuse me. Comma here. Okay, so that's the only change that we need to make. And now we're going to test it down here. So again, the test is going to be very similar to what we had on the previous, except we're going to get to see some new things here. So I'm going to copy and paste. This is very similar to what I had on last week's lab. The difference is that we have k equals 2. So when we call the Arnoldi step here, we need to make sure that we include k. So I said we have k equals 2 here. It's whatever we want it to be. And so we need to make sure that we have k, call the Arnoldi step and put k there. So when we run this, since we're only orthogonalizing, since k is equal to 2 and we're only orthogonalizing against the previous vector, the H matrix should have a very nice structure. And we see that it does. It is this tridiagonal matrix. And if we pick k is equal to 1, notice what we're going to get is just this, because we're only orthogonalizing with respect to the previous vector, this is what we get. And this is basically what we're going to get for the conjugate gradient algorithm. But when we do k equals 1, we're just orthogonalizing with respect to the previous vector. So it's only the hjj and the hj plus 1j that has a non-zero entry. But we can still see that it satisfies this Arnoldi relationship that it should satisfy. It should satisfy this Arnoldi relationship, or that should be equal to 0. anything involving orthogonality, which would be the VM transpose AVM equals HM, that's not going to be true because they're not doing complete orthogonalization. But this relationship is just based on the Arnoldi algorithm and how things get created, and it's not based at all on the orthogonality. The other thing to notice is that as I increase k, the number of non-zero diagonals is going to increase. So if I go up to 3 here, I'll have that. And if I go up to 4 here, I'll have this. And I think maybe if I round, we might be able to look at something a little bit different. Okay, so we have this rounded. If I make m go up to 5, okay, we have something like this. And again, if I start at 2, we can just verify. This just verifies that since H has the form that it should have, in other words, a tridiagonal matrix, then it just verifies that what we're doing is correct. So if I increase this to 3, whoops. Oh, okay, sorry. So when I had it at 3, I was expecting there to be more here. I think I missed that diagonal there. Or maybe for the previous A here, all of those were 0 or something. Anyways, so if I go to 4, it's going to grow on the diagonal a little bit more. And when I go to 5, it should be just a full sort of non-zero Hessenberg matrix, which is exactly what we have there. Okay, so that's great. Very straightforward, just a simple modification of the I-Arnoldi step. And the Lanchow step, very similar. It's going to be another very simple modification. Okay, so what we're going to do in the Lanchow step, there's a number of ways that we could code this. I'm going to show you how I'm going to code it. I'm just going to sort of start from scratch. One way to code this is simply to call your I-Arnoldi step with k is equal to 2. That's going to be the same exact thing. Now what I'm going to do, I'm going to be a little more explicit and make it look a little bit more like how we did it in class. So I'm going to have, again, we're going to do, if j is equal to 0, we've got to sort of initialize things. V, the first entry of V is going to be equal to R naught divided by NP dot ln alg dot norm R naught. And then, okay, we're going to turn row 1 and false. So there's one usable vector, and we did not get breakdowns. So there we go. All right, so now we're going to say wj minus 1 is going to be equal to a times v. It's going to be avj. So the last index j minus 1 is the last computed vector. So it's going to be like this. Whoops. So this tells us we want all the rows in the j minus 1th indexed column here. Now, if you look in the book, it says wj minus 1 or wj. I think I'm keeping it as wj, even though maybe it should be wj minus 1 because I'm doing wj minus 1 instead of wj because Python is 0 indexed, but the book is 1 indexed. Anyways, wj minus 1. If you look in the book, it says wj is equal to avj minus beta j vj minus 1. This is going to turn out to be the same formula, and I explained a little bit about why that is in the lectures. The reason is just that vj minus 1, or that vj is also going to be orthogonal. So well, let me just write this out. Okay, so h bar. So this is going to be the first h bar j minus 2, j minus 1. Okay, well, this is like the beta j. Okay, we computed beta j in the previous iteration. So using the symmetry of the matrix, this is h bar of h bar j minus 1, j minus 2. J minus 1, j minus 2. In the previous iteration, we already computed what this is. So we're good. We don't have to compute it again. And now we can say h bar j minus 1, j minus 1. Whoops. whoops, I keep typing the wrong thing, is going to be wj and then the inner product of wj with vj. So wj minus 1 at or times v. Okay, now here's what I'm saying. In the book, it says it defines wj minus 1 to be avj minus it would be beta j vj minus 1. Or in the notation here, it defines this to be this minus a constant here, v comma j minus 2. Okay, the reason that these two things are the same is because this vector is orthogonal to this vector. So when we do the inner product here, this is the inner product of this vector with that vector is just equal to 0. So that's why it works. Anyways, and so now what we need to do is we need to subtract off the projection of wj minus 1 onto the previous two vectors. So we're going to say wj minus 1 minus equals, we're going to have h bar, I don't know why I keep doing a p there, j minus 2, j minus 1 times the vj minus 2, like this, and I don't know why I did a parentheses there. So it's minus equal this, and then plus h bar j minus 1, j minus 1, and then times v j minus 1, comma j minus 1. So remember, wj, so if we look at 1 indexed, so not 0 indexed, so if we look at 1 indexed, wj is avj, and then we have to orthogonalize that against vj minus 1 and vj. Okay, so in 0 index, this means wj minus 1 is a times vj minus 1, and we have to orthogonalize against vj minus 1 and vj minus 2. So here is vj minus 2, here is vj minus 1. Okay, what are the inner products? Well, the inner products are just the hij. So that's what's happening here. So the inner product, let me make sure there's not a typo here. I think there's a typo here. This should be, well, it doesn't matter. J minus 2, there. So vj minus 2, this right here needs to be the inner product of avj minus 1 and vj minus 2. And that's exactly what this is. So in general, hij, or h bar ij, is going to give you avj vi. In this situation, a is symmetric, so we could do the things in either order, and it would be, mathematically correct at least. So that's what we're going to have here. And then again, what we're doing up here, we're just using the fact that h is symmetric, and h bar j minus 2, j minus 1 is going to be equal to h bar j minus 1, j minus 2. So remember, this is the row, and this is the column. And so in the previous iteration, we computed what hj minus 2 is. Okay. So that's what we're going to have there. That gives us wj minus 1. And now, h bar j minus 1 is going to be the norm of wj minus 1. So this is going to be equal to np dot linalg dot norm of wj minus 1. And then in the next iteration, this is going to be called right here. Okay, so in the next iteration, it'll be j plus 1. And so if j is equal to j plus 1, j minus 1 is equal to j. And if j is equal to j plus 1, j plus 1 minus 2 is going to be equal to j minus 1. Again, this is just because h is symmetric. Okay, and look at the see the lectures for why h is symmetric. Okay, and then finally the next column is going to be equal to wj minus 1, And then finally, we're going to return j plus 1 and false. Okay, now for testing here, I'm going to just copy and paste a whole bunch of stuff that we can test. So A is symmetric. So, or when we use a Landshaw's algorithm, A should be symmetric. And so in that case, unlike the incomplete method here, it should really be a complete method. And even though we're only orthogonalizing it against the previous two vectors, since A is symmetric, it means H is symmetric, and AVJVI is going to be 0 for most of the entries. And so when we test it here, I'm testing it with n is equal to 5, m is equal to 4. Notice that for A, I'm doing 1/2 A plus A transpose. This is going to give us a symmetric matrix. Not positive definite, but it will be symmetric. And then all of these other things here are just set up for running the Landshaw's algorithm. But we're going to do for J in range m plus 1, we're going to do the Landshaw's step. And so what we're going to see here is the matrix that we're going to get is going to be tridiagonal. It's going to be symmetric, and all of these measurements here are going to be close to 0. So notice when we do make large 3D problem, if Q is equal to n, it means the matrix is going to be n cubed by n cubed. So we're going to have a 125 by 125 matrix, and we're only making a Krylov subspace of size 4. So our matrix is going to be 4 by 4. And this is what we have here. I was hoping that this round would when I printed H bar, I was hoping the round would make that look a little bit nicer. I'm not sure why it isn't, but why it did up here. Okay, so let's just not round it and see what we get. Anyways, we can see that we do get a tridiagonal matrix, and we can see that it is symmetric. So these entries here are all equal to each other. And then if we were to make M get a little bit bigger, let's say 5, I don't think it's going to fit. Yeah, that's going to be annoying to look at. So, yeah, oh well. Let's see, maybe if I round. Maybe now if I round. Maybe if I round it here, it'll keep it enough to, well, whatever. Okay, so that part's not working. Let me get rid of this. Okay, but notice, whoa, holy moly, we got a problem. Oh, that was not what I was expecting. Wow, why is this all of a sudden not working like I need it to work? Holy cow, what did I do wrong up here? So, these entries right here should be close to 0. Since they're not close to 0, it indicates that I have made a problem, or I've made a mistake, which I guess is making a problem. Let me see what I have done incorrectly here. So this is probably one of those cases where people who are paying attention are like, dude, you are making a mistake, and you don't even realize it. So let's see, wj minus 1. I'm looking at the code I did before in my preparation. H bar j minus 2, j minus 1 is equal to h bar j minus 1, j minus 2. H bar j minus 1, okay, is equal to that. Here, I'm going to split this actually into two things here. Okay, so wj minus 1 minus equals. Okay, so let me do this one at a time so I can make sure that I'm doing it correctly. Okay, so wj minus 1. Okay, we've got h bar j minus 2, j minus 1, and then vj minus 2, and then j minus 1, j minus 1, j minus 1. Okay, good. Then j minus 1 is equal to that. Good. Oh, you know what? Here, I never divided, so wj minus 1 is equal to wj minus 1 divided by, here's a problem, h bar j minus 1. Okay. All right, so now things should work out a little bit better for us. Okay, so what we have here, this is AVM minus VM plus 1 h bar. So this is just the standard Arnoldi relationship that's going to be true whether or not we're doing full orthogonalization or not. But this right here, this is going to be true. Notice this is VM transpose AVM minus H. This is the thing that's true. That's equal to 0. That's only equal to 0, or we can only be sure that's equal to 0 in the case that the VMs are orthogonal, that the VM matrix is orthogonal. In other words, we're doing a full orthogonalization. And this is almost 0, so yep, that works out well here. And then VM, this is V transpose V minus I. If V is orthogonal, that is if we have actually done full orthogonalization, then V transpose V is going to be roughly equal to the identity matrix. And so this says the maximum difference in V transpose V in the identity matrix is this very small number here. Now, as I increase in here, you're going to start to see that the numbers are getting less small. Okay, so not quite yet. So let's do 15. Okay, get a little smaller. Let me jump up to 20. Okay, I'm just going to jump up to 50. So this is a 10 cubed by 10 cubed, so a 1,000 by 1,000 matrix. Okay, a little bit less small. Okay, let's get up to 100. Okay, so now for 100. We can see this part right here, which doesn't depend on orthogonality, is still very small. So that indicates that our algorithm is working properly. But these entries right here, which are true only for orthogonality, or we can only be certain that they're true for orthogonality, are getting bigger and bigger. So if I maybe go back to 50 here, okay, 75, do a little binary search here. Okay, and we can see that. Okay, in your own code, you can play around with this. Now I have observed that it's around the time not around the time, but around when when this m is equal to the square root of the size of the matrix is where problems start. Now the square root of 1,000 is around 30. So it's a little bit farther, but okay, this is something that you can sort of play around with. All right, so that was the third part test. Just to indicate, we just want to see, does this code work? Okay, before we apply this code in one of our Krylov methods, we just want to make sure that this is doing what it should be, and this is how we checked it. Okay, it also indicates that the other thing that this shows us is that even though mathematically all of these should be equal to 0, what we see happening actually is that because we are not doing perfect arithmetic and we're doing floating point arithmetic, we start to lose the orthogonality. We start to lose the global orthogonality. Even though mathematically it should be orthogonal, the floating point introduces errors, and those errors propagate and build up. Okay, so IOM cycle. Okay, so this is going to be good. This is going to be very similar to what we did before. So if you look at so hold on one second. If you look at one of the videos that I did last week, so for the main lab, I didn't do this cycle with the check every and the max chunks. But in the third lab video I made last week, I showed you how to modify this so you have this check every and max chunks. And if you didn't watch that video, I'll just explain to you what's happening now, and then you can go and watch it. Otherwise, I'm just going to copy and paste. Or after that, I'm just going to copy and paste my notes or my code from the previous one. So what we're doing in this method with the check every and the max chunks, every 100, each time we grow the size of the subspace by 100, we're going to solve the problem. If that's within our tolerance, we're going to just exit. We're going to return what we have. If it's not within our tolerance, we're going to do another 100 dimensions. If that's within our tolerance, we're going to do that, and so on and so forth. And max chunks is the number of those cycles that we want to do. So if max chunks here is equal to 2, we're going to grow our Krylov space to size to dimension 100. We're going to check what we have. If that's within the tolerance that we have decided, we're going to just return that. If not, we're going to do another cycle. and then that'll be the last cycle we do, since we have we have two different. The max number of chunks is equal to 2. In the video last week, I called this chunk size. I think check every I called chunk size. Anyways, I'm gonna put this back to 10. Okay, so you can look at the video from last week to get an idea of, or not to get an idea, but you can look at the video from last week to see how that got implemented. Here's what it is. So hold on one second. So I'm just copying and pasting what I did from last week, and that's exactly what I would expect you to do when you're implementing this. Just copying and pasting your code from last time. So we want IOM cycle. So here, instead of the Arnaldi step, it's going to be the iArnaldi step. And we have to remember that we need to pass it the K. So this takes a K. We're going to pass the iArnaldi step a K. Where are we here? Okay, K. And that's it. That's all we have to do here. So it's going to be very simple. It's a very simple change. There's 2 changes that we're making to the IOM cycle. One is this thing with the check every and max chunks. You can look at lab 3 from last week to see how to make that change. And the other thing that's sort of the main thing from this week is that we're calling the iArnaldi step instead of the full Arnaldi step. Okay, so let me just, okay, good. All right, and now FOM symmetric. Again, this is going to be very, very similar to what we had last week. Same thing here, okay, except same thing with the chunk size and the max chunks. Again, you can look at the previous lab video to see how we're going to implement that. But the only difference, hold on one second. And again, I would just expect that you're going to be copying and pasting a lot of code from last week, which is why I'm doing that here. Okay, this is what we have. The only difference is down here, instead of calling the Arnaldi step, we're going to call the Landau step. And that is literally the only difference. So you can see that this is the only difference from last week in lab 3. I did the FOM with the chunk size and the max chunks. The only difference between that and this is that instead of calling the Arnaldi step here, we're calling the Landau step. Okay, now I'm going to code this conjugate gradient first, but I just kind of want to make sure that everything I've done so far has been correct. And so I'm going to test that now. So I'm going to do n is equal to 20 here. And then I'm going to do a, b, x, true is equal to make large 3D problem, and I'm going to say q is equal to n. Okay, and I'm going to first test the just the IOM, the incomplete orthogonalization method. I'm just going to copy and paste code that I had basically from the last time. IOM cycle, so starting the timer here. Actually, if I want to be precise, I need to start it here. Okay, I'm saying k is equal to 5, n is equal to 20, k is equal to 5. This is going to be the IOM cycle. I'm going to check every 10 and only going to do 100 cycles or 100 chunks. So it's going to be at most, I'm going to build the space to at most 1,000, dimension 1,000. But notice what I'm doing. I'm only orthogonalizing against the previous 5 vectors. So I'm going to actually change this a little bit. I'm going to start by orthogonalizing against the previous 50 vectors. Now, we are building a subspace at most size 1,000. So if I'm still only checking against the previous, or if I'm still only orthogonalizing against the previous 50 vectors, that's still pretty good. With n is equal to 20, we're going to have a 1,000, or sorry, an 8,000 by 8,000 size matrix. I'm actually going to go to, well, I'm going to keep it at 20. Okay, I don't think this is going to take very long to run at all. Okay, of course. Oh, I didn't import time. There might be another problem here that I forgot to do. So import time, and I need to import SciPy as SP because I'm going to have some systems that I solve. Okay. Okay, this is great. So IMO, that should say IOM. It's another one of my little rearrangements. So what we're doing here, we're doing 60 iterations. This is the time. Took almost 1/10 of a second. Okay, for n is equal to 20. So this is an 8,000 by 8,000 matrix. We got up to a dimension 60 subspace, and we are orthogonalizing against the previous 50 vectors. So this is still almost like a complete orthogonalization method. It's only the last 10 vectors that are not completely orthogonalized, and then it's not missing a whole lot. But notice what happens if I make this go down to k is equal to 5. Actually, let's do maybe 25. Okay, notice the number of iterations grew, and the time grew here, but I'm only orthogonalizing against the previous 25 vectors. Okay. So I think when I did 50, I'm a little bit surprised that... okay, so now what I'm going to do is I'm going to go down to 5. So I'm only going to be orthogonalizing against the previous 5 vectors. And notice what happens here. It actually took fewer iterations. That is very strange to me, that this is taking fewer iterations. Well, even better. But it only takes 0.05 seconds, and I can go down to k is equal to 2, and more iterations, more things here. Now, this is just experiments. You can sort of play around with this and see exactly what's going to happen. All right, so now what I want to do is I want to test the symmetric, the FOM symmetric algorithm. So I'm going to make AS, that stands for symmetric, asymmetric, and it's going to be 0.5 times A plus A transpose, and then BS is going to be equal to AS times X true. Whoops. X true. And I'm going to copy and paste this here. And here, instead of IOM cycle, it's going to be FOM symmetric. And that does not take a K, so I don't need to have this K here. Now, this is not going to be IOMK, it's going to be FOM. Okay, so X true minus XM. Okay, I think this should work properly. Oh, hold on. You know what? This should be check every. You guys are probably... This is another time where you guys are like, wait, what's going on here? Sorry about that. Okay. So all of the rest of the code is fine. I just had max chunks, which is still what I had left over from the previous week's video. All right, so let's run this again. Clearly there is a problem here. So what is the problem? Because so what have I done here? I've run the symmetric algorithm on a non-symmetric thing. So the fact that it's symmetric is important. So I need to change this to AS and this to BS. Remember, like for the H matrix, we're using the fact that A is symmetric to sort of simplify some computations. Now, if I had just called, in my FOM symmetric, if I had just called my I Arnoldi step with K is equal to 2, this wouldn't have been as bad as it is. But anyways, let's try it again. Okay, so here we go. Get this error small here, get the error small here. I think an interesting thing that well, okay, no, never mind. I'm misreading this. So for n is equal to 20, the symmetric, if I run the FOM symmetric, so the full orthogonalization symmetric, takes 0.02 seconds, and then it's going to be 0.1 second and 260 iterations for the incomplete orthogonalization method. I don't know what happens if I change this to 5, if I get something different. Okay, so again, I'm not going to play around with this anymore, but I think it's interesting, and it's definitely something that you can play around with on your own. All right, so finally, last thing we're going to do, we're going to look at the conjugate gradient algorithm. This is the last thing that we're going to do tonight. Again, a lot of what we're doing tonight is simply it's simply copying and pasting from last week. This is going to be the first thing that's kind of new. So the first thing that we're going to do is if x naught is none, we're going to go ahead and initialize it. And we're going to say x naught is equal to np dot zeros. And it needs the number of entries here needs to be the number of columns of A. So we're going to say shape 1. Okay, now we're going to look at what the first residual is going to be. R0 is equal to B minus A times x naught. Okay, very similar setup to what we've done in the previous methods. And now we're going to have B norm. We need to save this. B norm is going to be equal to np.linalg.norm. We don't actually need to save it, but we want to not have to compute it. Like, we're not going to overwrite B. We're not going to overwrite the norm, but we don't want to have to recompute this again. So we're going to leave it how it is. And then similar to what we did for the other ones, this is going to tell us when to stop. Target is going to be the max of the absolute tolerance and the relative tolerance times B norm. Okay. And now, what happens if we kind of are already there? So if np dot linalg dot norm of r naught is less than or equal to target, we're done. Okay, we just got lucky. And we're going to return x naught, which is the, okay, that's the x that we're on now. Beta, you know what is beta equal to? Beta is equal to np dot linalg dot norm r naught divided by b norm, and then it took 0 iterations. So oh, you know what, I have this backwards. So to keep things consistent with how I had it in the other ones, I'm going to change this. Feel free to do that on yours as well, or keep it the same, it doesn't matter. We did 0 iterations. Okay, so this is kind of what the setup, and then what happens in the case where we just happen to guess the right vector here. In other words, we passed in the correct vector. Okay, not very exciting. That's not the exciting case or the interesting case. And so now what we're going to look at is going to be this. Oh, hold on. Okay, sorry. I had a little bit of a panic attack there because I thought that I was not recording. But I see that I am. Okay. Where are we here? Okay, so now we're going to start the main loop in the CG algorithm. So we're going to set some stuff. J is going to be our counter. We're just using this to count the number of iterations. Notice this has a max iter, which default at 1000. Okay, and then R is going to be equal to R naught. That's what we're going to continually update. P is going to be equal to R naught. That's the P vectors that we're going to continually update. And then X is equal to X naught. That's the X vector that we're going to continually update. And now what we're going to do is we're going to say while J is less than max iter. And now we're going to have our main loop here. Okay, so you might want to look at the algorithm, at the CG algorithm as we go over this. So first we're going to increment J. Okay. And now there's several times where we have to compute APJ. So I'm just going to call that AP. So AP is going to be equal to A times the current value of P. Okay, if you look at the algorithm, it's APJ is what gets used. So AP is going to be equal to A times PJ. And then also several times we have to compute RJ times RJ, or the inner product of RJ with itself. And I don't want to have to do that too many times. I just want to do it once. So I'm going to say RR is equal to R times R. And remember, this at symbol is overloaded in such a way that it does whatever the defined operation is. So R is a vector, R is a vector. So R at R means the dot product. A is a matrix, P is a vector. So A at P means just do the matrix vector product, A times P. Okay, and then AJ, I'm just going to call A, or alpha J in the algorithm. I'm going to call this A here. This, remember, is the inner product of RJ with itself divided by APJ, or sorry, divide is AJ is the inner product of RJ with itself divided by the inner product of APJ with PJ. So RR is the inner product of R with itself, and we're going to divide by the inner product of PJ with APJ. So PJ is just P is the current value of P, and then APJ is just AP. Okay, now I could have here again like A at P, but now I'm computing that same product, and I don't want to do that. A is a big matrix. It's a sparse matrix, but it's a big matrix, and so I only want to do that computation once. So I'm going to divide this, or not divide, multiply this by AP. Okay, now I can update my value for X. So X is going to be equal to X plus, remember it's AJ times PJ. So this is AJ, so A and PJ is just equal to P. It's the current value of P. So I could do either X equals X plus or X plus equals. To be a little more explicit for the lab, I'm going to write it like this. Okay, that's good. And now what we're going to do is we now have to update our values of R and P and, well, that's it, I think. Okay, so the only time where we have like, the only expression where we're using both the current value and the previous value is going to be for beta, for beta j. Beta j, remember, is rj plus 1 over rj. That is, beta j is equal to the inner product of rj plus 1 with itself divided by the inner product of rj with itself. So I'm going to introduce the next value of r, the new value of r, that is the new residual. The new residual is going to be equal to r minus a times ap. That's just rj. So this says rj plus 1 is equal to rj minus aj. Let me say that again. Rj plus 1 is equal to rj minus aj times apj. That's all this says. What is r? It's the current value of r. A, I already mentioned, is aj, and then ap is a times p. Okay. So that's the new value of r, and then the new value of beta, I'm going to call it bj for beta j. I did call it b before, but I'm using b up here. B is the right-hand side, so I don't want to overwrite it. And I don't want to use, well, sorry, you know what? I'm just going to use beta. So sometimes beta means the norm of R naught, but I'm going to use it in this context. Beta j in the context of the CG algorithm is equal to the inner product of rj plus 1 with itself divided by the inner product of rj with itself. So we're going to have in r at in r, and we're going to divide by r at r. Whoops. We're going to divide, wow. We're going to divide by r, the inner product of r with itself. But remember, we've already computed that. So I'm just going to write this as RR. And if I have, I don't need parentheses if I have it like this. And then now we can update P. So P is going to be equal to the RJ plus 1, that is in R, the new R, plus beta J, so beta, times PJ. Or just times P, sorry. So now we have the updated P. And again, I could, well, okay. I could write this a little bit differently, but I'm going to keep it like that. Okay, so now what I need to do is I need to compute the norm of the new residual. If that's below our tolerance, then I'm done and I can return. Otherwise, I need to keep going. So if R norm is going to be equal to np dot linalg dot norm of R0, sorry, not R0. What am I doing? In R. Oh, sorry. One other thing. I need to now update R. So R is going to be the new value of R. So there we go. Okay. So norm is going to be, R norm is going to be the norm of R. That's the norm of the current residual. And so now we're going to say if R norm is less than or equal to target, then we're going to, We're going to return the current value of x. We're going to return the relative residual. That is R norm divided by B norm. And the current number of iterations, which is J. Okay. And now if we can exit this loop in two ways. One is by exiting the function when R norm hits the target, or if J reaches the max iterations, in which case we're going to return X R norm over B norm, and then J. There we have it. Okay, and so now I want to test it. Now remember, to use a conjugate gradient, it's not enough that the matrix is symmetric. It needs to be symmetric, positive, definite. So to make a symmetric, positive, definite matrix, I'm going to say ASPD is equal to A times A transpose. Okay, this gives us a symmetric, positive, definite matrix, and then BSPD is going to be equal to ASPD times X true, right here. All right, and now let's see. I'm just going to copy and paste some stuff here. I'm sure there's going to be an issue because there always is when I try to make it easy. So we're going to have CG here. This needs to be ASPD. This needs to be BSPD. And then for CG, it's just max iter, I'm going to say, is equal to, I don't know. Well, I'll do the default 1000. I don't have to put that there. It would default to 1000, but I might want to change it. And then I'm going to do CG here. Okay, now the question is, how many errors are there going to be? And how many errors have you guys caught? Hey, that was almost an error. Okay. All right, X true is not defined. Oh, forgot the underscore. Okay, let's hope that's the only one. Okay, and again, we can see this is very nice. It has converged. We can see the error is small here. 10 to the minus 8, and took 160 iterations for the conjugate gradient. I think it's interesting that the FOM symmetric only took 70 iterations. I mean, to me, that's just an interesting. I mean, it's different. It's being run on different matrices. So we have this, but now I'm going to actually look at this. So ASPD is also a symmetric matrix. So I want to compare that. I want to compare FOM symmetric on a symmetric matrix, on a symmetric positive definite matrix with conjugate gradient. I think it should basically be the same. So I'm going to have ASPD and BSPD. And notice we're not doing any sort of preconditioning here either. All right, so let's do this. Okay, yeah, so we see it's basically going to give us the same exact thing, very, very close answers here, which is exactly what we should expect, because the conjugate gradient algorithm is essentially just another way to derive the FOM symmetric matrix, or the FOM symmetric algorithm, but in the specific case where A is sparse and positive definite. And all of these are running extraordinarily quickly as well. So it's very nice. I think we can even bump this up to, let's see what happens if we bump this up to, well, not 500. If we bump this up to 50, I think when I did an experiment, it might have taken about 20 seconds for it to run, but I don't remember for sure. Oh, it's almost done here. Okay. So, yeah, so the FOM symmetric algorithm, it's surprising to me that it took 590 iterations. Oh, I bet that's simply because we were doing check every at 10 instead of 5. I assume maybe if I check every at 5, I think probably something else is because when we do the checks for the FOM symmetric, that takes a little bit more time. I'm surprised that it takes twice as long to run. Going to 5 more iterations, I think, is just because we were checking every 10 instead of 5. Well, that's really interesting. That is... Oh, we have bad convergence here as well. Oh, with we're just barely converging here. Oh, are we maxing out our iterations here? Yeah, we're maxing out our iterations. That's why. But here, we're not maxing out our iterations, but we're still... okay, so let's... For conjugate gradient, let's see what happens if we bump that to 10. It's going to take a little bit longer to run. I don't know if we'll max out the iterations. Okay, there we go. But we did, look, we maxed out the iterations, but it looked like we got there anyways. Okay, so here, I'm gonna, okay. Yeah. Okay. So there we have it. And we still haven't. Well, we didn't max out our iterations, but okay. So one last experiment. I'm going to change this to 10 to the minus 10th, and now everything should be converging like it should. Okay, but look at how well the IOM method is performing on A. Look at how well IOM5 is performing on A. The symmetric and the sparse, the AS and the ASPD are nicer matrices than A, which is one of the reasons that it's the A matrix is nicer than the symmetric matrix and the sparse positive definite matrix, which is why it's running a little bit faster. But I'm surprised that. So the FOM symmetric on the sparse positive definite matrix looks like it's getting hung up a little bit. Okay, well, at any rate, at least when I have the tolerance up to here. So this is the method. These are all of the methods that we're looking at. This gives you enough to do the homework for sure. And like I said, I would imagine that a lot of what you're going to be doing for this homework assignment is just copying and pasting your previous week's homework assignment. And then just making the modifications that need to be made. Okay, that is it for this video. I don't know how much longer this is going to take, and I don't want to wait. So that's it.